Well, hello everyone. I am Snigdha Kakkar and this is my channel Accelerate AI Careers. Today we are going to solve a very interesting lead code problem, lead code 64, minimum path sum. It is one of the all-time favorites for companies such as Amazon and Google, and they have asked this in their last 6 months of interviews. It is quite similar to unique paths 2, which we did yesterday. It is a dynamic programming question. Let's see what does this question say. So you have been given an m cross n grid, you have m rows and n columns filled with non-negative numbers, that is only positive numbers. You have to find a path from the top left value, that is top left cell, that is grid 0, 0, to the bottom right, that is grid m minus 1, n minus 1, such that the path minimizes the sum of all the numbers along its path. That is, you have to choose that path which has the minimum number of sum, okay? You can move only in two directions, either to the right or downwards. You cannot go to the top or to the left or to the diagonal direction. That is, you cannot go backwards or in diagonal. So you have only two choices to make at every point of time. Either you can go towards right or you can go downwards. So if we think about a brute force way of solving this question, one might think that I will start from this cell and then I'll choose whether this is minimum to the right or this is minimum to the downwards and choose accordingly. Then from the downward cell, I will again make two choices, either to the right or downwards. And I'll keep on making those choices until I reach the last cell. And my decision would be like a decision tree, and every cell I would be making one of those two choices, and there could be multiple paths to follow. So the time complexity for such a solution would be O of 2 raised to power n, that is an exponential time complexity, which is not that great. But we can optimize it. We can optimize it by caching. So we can recursively move from one cell to the another cell and make those choices. But we can keep on saving the optimum path sum from each cell to the bottommost cell again and again, so that we do not have to compute it whenever we need it. If we have visited that cell and we have computed the optimum path, then we have saved it in our matrix there. So recursively, we keep on making those choices and we do not need to calculate again and again the optimum path. We have computed it and cached it and used that. So in that case, your time complexity would reduce from the exponential value to O of m into n, where m into n is your size of the grid or matrix. And your space complexity would also be O of m into n, because you are using a matrix of the same size to cache the optimum path from each cell to the bottommost cell. So this is your one way to solve, which is recursive solution. But if you pay heed to this solution, instead of starting from grid 0, 0 and finding the optimum path to reach grid n minus 1, n minus 1, you can start from this bottommost cell and find optimum path to reach this cell just from the nearby cells, right? And then go backwards. And then go backwards in the row, go backwards in the column, and finally reach this cell grid 0, 0. That way you will be able to find the optimum path going from grid 0, 0 to grids m minus 1, n minus 1, but you will be finding it going backwards. So this is a classic case of dynamic programming, and let's see how we can solve it. So here, this is my given example 1, and I have taken this matrix of the similar size to calculate my DP, that is my dynamic programming matrix here, the values here. And I will initially assume that all the out of boundary items here and all the out of boundary cells here will have cost as infinity to reach this value in the bottommost corner, because you cannot come back from there, right? And in this values, in this cell right below it, I would assume the cost is 0, because you are right there, right? Because either you can go downwards or to the right, so you are there at that cell, so you can assume the value there at 0 initially. Okay, rest everything I can assume as infinity. Now I will start backwards. To start backwards, I will first start from this cell. So starting from this cell, the cost would be the value to the right, which is infinity, the value to the bottom, which is 0, minimum of them. So minimum of 0 and infinity is 0, and adding the value in the current cell, which is 1. So 0 plus 1 is 1, which I have placed here. Now we need to compute the value just to the left of it. So this cell, it would be this cell's value itself, that is 2, plus minimum of the value to the right, which is 1, and the value to the bottom, which is infinity. So 2 plus minimum of 1 and infinity, which is 1. So 2 plus 1, which comes as 3. And you will keep on computing this way all the values. So I'll show you one more value, say value here, just to the left of 3, okay? So to do that, we will take the value in this current cell, which is 4, and minimum of the value to the right, which is 2, and to the bottom, which is infinity. So minimum would be 2, and so 2 plus current cell value, which is 4, it comes out to be 6. So this cell will have 6, and so on. So you can compute the entire DP matrix, and whatever value you get here, that ways you can get the sum of the most optimum path. Okay. So that is one way to go about this solution. But in this case, your time complexity would be O of Mn, where M is your number of rows, N is your number of columns. And your space complexity would also be O of Mn, because you're using the entire matrix to store these values. You can optimize the storage for sure to just the number of rows, that is O of M or O of N. How you can do that is, because for computing this particular row, you need just the values to the bottom of it. You don't need 2 or 3 rows below it, right? Same ways, to compute the second row values, you just need the row below it, and so on. So you can replace that row values in place in your DP row. Rather than taking a matrix, you can initialize a row and return the row. I'm not going in depth of this solution because I've explained the solution in very detail in my last video for unique paths too. So you can look at it to see how to go about that for optimizing the storage. But instead of taking the entire matrix of M by N dimensions to store the DP values, we will just be taking a row having N columns to store the DP values, and we will be replacing them in place as and when we are updating. And finally, we can return row 0 because we just need the value of grid 0, 0 to be returned. I hope you understand this. Now let's start coding it. So I'll first initialize my rows and columns. And how do I initialize this? Rows I can initialize by length of grid, and columns I can initialize by length of grid 0. Then I can initialize my result variable, which will go for float. So I have to initialize everything by float infinity as I indicated, except the bottommost cell. So float infinity into number of columns, which is columns plus 1, right? And I would be doing that for our rows in range rows plus 1. That's how we initialize it in Python. Okay. Now I can reset the bottom column, which is rows minus 1 columns, to 0. Rest everything can be set to infinity, as I explained in the algorithm explanation. Now I will go reverse. So for R in range, and how do we go reverse? Rows minus 1, that is my starting point, reaching till minus 1, and step size would be minus 1. That's how you go reverse, okay? Same way I can go reverse in column. For C in range, I have to use everything small. So for C in range, columns minus 1 till minus 1, take step minus 1. That's how you go reverse here. And you can calculate result RC, that is the DP value everywhere, by grid RC, that is the current value in the grid at the same position, plus the minimum of result at R plus 1, that is just below, and result R C plus 1, that is just to the right. So you will take the minimum of it and add it to the current grid value, and that's all, and you can return the result. And what do you return the result for? Grid 0, 0, so you will return just result 0, 0. You can even optimize this solution more, like I mentioned, by following the same solution I explained in unique paths 2. By instead of initializing the entire matrix of M by N like I have initialized here, instead of initializing that, you just initialize one row and you keep on replacing it in place and return result 0. So let's run this and submit. So it's accepted. Let's submit. So as you can see, the solution is quite good. I can briefly explain and summarize it to you again. We first initialize rows and columns by length of grid and length of grid 0. Then we initialize a result variable for columns plus 1, rows plus 1. And I initialized the bottommost cell with 0, rest everything I initialized with infinity. Then we started moving backwards in rows and columns like I did in the algorithm explanation. And we update every cell's DP value by current cell's grid value plus minimum of the cell's value just to the right of it and just below it as computed in our DP matrix. And we keep on doing that in the entire loop, and finally we return result 0, 0, that is value at the top left cell, which we need, and once we return it, our entire solution is done. So I hope you like this solution. If you have a better way of solving this, share it in comments. If you have any doubts, ask them in the comments. I'll be happy to address it. If you like my way of solving lead code problems and want to solve questions with me, subscribe to my channel to get your daily lead code challenge updates. Thank you.